Okay, picture this. You've got this incredible multi-million-dollar machine. It's carving a block of titanium with surgical precision. It's amazing. But then, one single invisible typo in its code turns that absolute masterpiece into a totally worthless piece of scrap metal. Yeah, that's the high-stakes world of CNC machining we're diving into today. The hidden dangers lurking in your code.
All right, so let's set the scene. In modern manufacturing, the stakes are just incredibly high. We're not just talking about being accurate anymore. No, we're talking about a level of perfection where a single micron, that's smaller than a human hair, can be the difference between a breakthrough and a complete disaster.
And look, don't just take my word for it. The folks over at Machinery and Manufacturing put it pretty bluntly. Any programming error is going to be costly. And when they say costly, they're not kidding. We're not just talking about wasting a bit of metal. We're talking about catastrophic failures. Destroying super expensive, irreplaceable tools, damaging the machine itself, and basically bringing your entire production line to a screeching halt.
So, what's the core of the problem? Well, think of it this way. On one side, you have the design from your CAM software. That's the architect's blueprint, right? It's the beautiful vision, the what you want to make. But on the other side, you have the G-code. Those are the line-by-line instructions the machine actually follows, the how. And there's this gap, this translation from the dream to the reality. And that's exactly where the errors, the gremlins, love to hide.
So let's talk about these gremlins. Where do they even come from? Well, you've basically got two types. You've got your physical gremlins, the ones you can actually see and touch, lurking in the machine itself. And then you have the digital ghosts, the ones hiding in the code.
Okay, first up, let's talk about the physical stuff, like backlash. Imagine a tiny bit of looseness in the gears of the machine. It's just a microscopic amount of wear and tear from being used all the time. Now that might not sound like a big deal, right? But when that tool is spinning at thousands of RPM, that little tiny imperfection, it creates vibrations that can totally ruin the surface finish of your part. All that precision, gone.
And it's not always the machine's fault. Sometimes the material itself literally fights back. We're talking about deformation. All the heat and force from the cutting process can actually cause the workpiece to warp, to bend, to distort. It's kind of like a piece of plastic you left out in the sun. All that hard work, all that precision, just ruined because the material decided it didn't want to cooperate.
And then you've got the digital ghosts. These are the sneaky ones, the silent killers. This is where you get a G-code mismatch. See, you might think G-code is a universal language, but it's not. A command that means go left on a FANUC controller might mean something totally different, or nothing at all on a Siemens machine. And when that happens, you get totally unexpected actions with disastrous, unpredictable results.
So here's the scenario that every machinist dreads. You've spent hours, maybe even days, perfecting your design. You've run the simulation a dozen times. You've watched that virtual toolpath glide through the material over and over, and everything looks absolutely perfect. It's like this digital ballet of precision.
And then you press the big green Go button on the real machine. And what you get isn't a masterpiece. It's a pile of expensive scrap metal. And you're just standing there with this sinking feeling, asking yourself that million-dollar question. So why did this happen? What went wrong?
Okay, before we jump into all the super high-tech solutions like AI and digital twins, let's talk about the operator's first defense. This is ground zero. Because sometimes the absolute best tool you have is a pair of experienced eyes and a very steady hand.
You see, experienced operators have a couple of essential safety checks, a couple of tricks up their sleeve. First, there's single block mode. This lets them execute the G-code one line at a time. It gives them total control to inspect every single move. Then there's dry run mode. This is where you run the whole program, but with the tool way up high, safely above the part. It's like watching the machine dance in the air before it ever touches the metal.
And a dry run is more than just watching the machine move around. It's a whole procedure. You take the workpiece out, you run the program nice and slow, and you just watch. You're looking for potential collisions, clearance issues, any weird or unexpected toolpaths. If you spot anything, you hit stop, fix the code, and start over. It's all about catching those subtle errors that could lead to a huge failure, and building confidence in your code before you even think about cutting a single chip.
Now, look, these manual checks are absolutely vital, but let's be real. For the incredibly complex parts we're making today, with super high-speed machining, we need something more powerful. We need a way to simulate reality, to basically see the future before it actually happens.
So, here's the big question, right? How can we find these hidden errors without risking the real machine? How do we bridge that gap between the perfect, clean world of the digital design and the messy, unpredictable reality of the factory floor?
And the answer is something called a digital twin. Now, the easiest way to think about this is like a flight simulator, but for your CNC machine. It's a perfect virtual copy of the entire machine and the whole process. This thing simulates the final G-code, not just the pretty toolpath. It lets you test everything in a completely safe environment. You can crash and burn all you want in the digital world, and you won't put a single scratch on your real machine.
And this is the key difference, you guys. A standard CAM simulation, that just simulates the intended toolpath from your design file. It doesn't see errors that happen later. But a digital twin, or G-code verification, that simulates the actual G-code that the machine is going to execute. It catches those post-processor errors, and it models the machine's real-world movements. So one checks the idea, the other checks the final real-deal instructions. Huge difference.
And here's where it gets really powerful. This advanced analysis can actually link a visual flaw on the simulated part, like a gouge or a scratch, directly back to the specific line of G-code that's causing it. So it doesn't just say, hey, there's a problem. It says, hey, the problem is right here on line 257 of your code. Go fix it. It's an absolute game changer.
Okay, that's amazing. But what if we could go even one step further? What if the machine could become self-correcting? What if it could not only find the problems, but actually prevent them from happening in the first place?
Well, that's the future we're heading towards. We're moving beyond just simulation into real-time sensing and autonomous correction. Systems like something called NeuroPID-CNC are using a whole network of sensors to create a live feedback loop. They're monitoring everything, temperature, force, vibration, and using that data to predict and then mitigate problems like deformation as they are happening. It's like the machine is thinking for itself, making tiny corrections on the fly to ensure a perfect part every single time.
And the results? They're really impressive. The research shows that this NeuroPID-CNC model, for example, is significantly better at predicting these risks than other, more conventional algorithms like random forest or SVM. I mean, look at that comparison. We're not talking about a small improvement here. This is a huge leap forward in our ability to predict errors before they happen. So this brings us to a really fascinating question. If machines can start to predict and even prevent their own mistakes, what does that actually mean for the future of making things? We're moving away from simple error detection and into this new world of real-time, intelligent error prevention. It completely changes the landscape, turning our machines from just tools into intelligent partners. It really makes you wonder, what comes next?